to Science Aura, I am Dr. Sachi Vale. Up in the boundless skies, a silent but profound revolution is taking shape. For decades, the ultimate prize in aerial combat has been absolute invisibility. Modern stealth fighter jets are absolute marvels of engineering, meticulously designed to slip through enemy radar and sensor defenses completely unnoticed by anyone. But what happens when the very laws of physics are weaponized to strip away this carefully crafted cloak of invisibility? We are currently standing on the precipice of a brand new era in military technology. The traditional methods of hiding from infrared sensors and thermal tracking are about to face an unprecedented challenge from the bizarre and fascinating quantum realm. To truly understand this monumental shift, we must first look at how modern air combat operates today. The sky is no longer just a physical battleground. It is a complex electromagnetic arena. Aircraft project signatures across various spectrums, and the primary goal of stealth technology is to minimize these signatures, making the aircraft blend seamlessly into the background. Radar cross-sections have been drastically reduced using specialized geometric shapes and advanced radar-absorbing materials. These innovations have made it incredibly difficult for conventional radio frequency radars to detect an incoming threat. However, radar is only one piece of the puzzle. The other massive challenge in remaining undetected is managing thermal emissions. Every machine that operates generates heat, and a high-performance jet engine generates a colossal amount of it. This heat creates a massive infrared signature, a glowing beacon in the cold expanse of the upper atmosphere. Heat-seeking missiles, or infrared homing missiles, have been designed specifically to lock onto these intense thermal hotspots and track them relentlessly. The science of thermal evasion has evolved significantly over the years. Aerospace engineers have developed intricate exhaust cooling systems, mixing cold ambient air with the scorching exhaust gases before they leave the nozzle. They also bury the engines deep within the fuselage to shield the hottest components from being viewed directly from below or from the sides of the jet. Despite these brilliant engineering feats, completely eliminating a thermal signature is physically impossible. The friction of the airframe slicing through the atmosphere at supersonic speeds also generates substantial heat on the leading edges of the wings and the nose. Therefore, modern fighters must also rely on active countermeasures to survive against thermal tracking. When an incoming heat-seeking missile is detected, pilots deploy flares. These are essentially intensely hot pyrotechnic payloads ejected from the aircraft. The goal is to create a sudden, brighter, and more attractive heat source that distracts the missile's infrared seeker, tricking it into following the falling flare instead of the actual aircraft's engine exhaust plume. This cat-and-mouse game has defined aerial survival for decades. Missile seekers became smarter, using dual-band infrared sensors to distinguish between the unique spectral signature of a metallic aircraft and the burning chemicals of a flare. In response, countermeasures became more sophisticated, utilizing lasers to blind the missile seekers in a technique called DIRCM. Directional Infrared Countermeasures, or DIRC, fire tightly focused beams of laser energy directly into the delicate optical sensors of the approaching missile. This overwhelming burst of light confuses the tracking algorithms, causing the missile to veer off course. It is a highly effective defense mechanism, but it still relies on the classical principles of physics and optics. But the landscape of warfare is never static. As defensive technologies reach the absolute limits of classical physics, offensive technologies are looking elsewhere for a breakthrough, and they have found it in the most fundamental building blocks of the universe. We are talking about the realm of quantum mechanics, where the ordinary rules of reality simply do not apply anymore. Quantum mechanics describes the behavior of matter and energy at the atomic and subatomic levels. Down here, particles can exist in multiple states simultaneously, a phenomenon known as superposition. They can also become inextricably linked across vast distances, a property known as quantum entanglement. It is this specific property that is poised to change everything we know. Imagine two photons, the fundamental particles of light, created together in such a way that their physical properties are perfectly correlated. If you measure the polarization of one photon, you instantly know the polarization of the other, regardless of whether it is an inch away or on the other side of the galaxy. Albert Einstein famously called this spooky action at a distance. This spooky action is the foundation of quantum thermal imaging and quantum radar. Instead of simply passively looking for the heat emitted by an aircraft, A quantum missile system actively probes the environment using entangled photon. It generates pairs of these linked particles, keeping one half of the pair safely inside the missile's sensor array as a reference point. The other half of the entangled pair, the signal photon, is broadcast out into the airspace ahead of the missile. These signal photons travel forward at the speed of light, scanning the sky. When they strike an object, such as an enemy stealth fighter, they bounce back toward the missile. This is where the magic of quantum mechanics provides an insurmountable advantage. In a traditional radar or LiDAR system, the receiver has to filter out immense amounts of background noise, solar radiation, and active jamming signals to detect the faint reflection of its own pulse. It is like trying to hear a whisper in a hurricane. Electronic warfare systems exploit this by flooding the environment with fake signals, completely overwhelming the receiver. But a quantum sensor operates differently. When the returning signal photon enters the sensor, it is immediately compared against the idler photon that was kept behind. Because they are entangled, they share a unique, unforgeable, cryptographic connection. The system checks for this correlation. If the connection is verified, the system knows with absolute certainty it is real. Any photon that does not share this specific quantum entanglement with the onboard idler photons is instantly discarded as background noise or deliberate interference. This means that flares, thermal decoys, and sophisticated laser blinding systems are completely rendered useless. The quantum sensor simply ignores them, seeing straight through the chaotic electronic battlefield. Furthermore, any attempt by an enemy system to intercept, measure, or alter the outgoing signal photons will irrevocably break their fragile quantum state. This phenomenon, known as quantum decoherence, instantly alerts the missile that it is being tampered with. The act of observation itself destroys the entanglement, making quantum signals fundamentally unspoofable. By utilizing this unbreakable quantum key, these future missiles can paint a highly detailed, deeply accurate thermal and physical image of the target. They can distinguish the exact shape of a stealth fighter from a flock of birds or a cloud bank, regardless of the stealth coatings or thermal suppression technologies employed. Invisibility becomes a thing of the past. The implications of this technology for global military strategy are absolutely staggering. The current generation of 5th generation and upcoming 6th generation fighter jets cost hundreds of millions of dollars each. Their primary defense mechanism is their low observability. If quantum sensors can effortlessly detect them, these expensive assets become highly vulnerable. This shift represents a fundamental resetting of the balance of power. A nation equipped with advanced quantum missiles could effectively neutralize the stealth capabilities of its adversaries. The skies would no longer belong to those who can hide the best, but to those who can see the most clearly through the complex web of modern electronic and thermal countermeasures. However, transitioning this theoretical physics marvel from a pristine laboratory environment into a functional weapon system mounted on a supersonic missile is a monumental engineering challenge. The hurdles are immense, and they revolve primarily around the delicate nature of quantum states. Quantum entanglement is incredibly fragile and easily disrupted by the environment. To maintain the entanglement of the idler photons on board the missile, the quantum memory and processing units must be isolated from all external interference. This usually requires extreme cryogenic cooling, bringing the components down to temperatures near absolute zero. Achieving this inside the cramped, vibrating, and intensely hot body of a missile in flight is daunting. Miniaturization is the key to making this a reality. Engineers must shrink bulky laboratory equipment, lasers, beam splitters, single photon detectors, and cryogenic coolers into a compact, rugged package that can withstand the immense G-forces of a missile launch and high-speed maneuvers. Every gram of weight and every millimeter of space must be perfectly optimized. Another significant obstacle is the generation rate of entangled photon pairs. For a missile moving at Mach 3 or faster, the sensor must process information incredibly quickly to update the target's position. Current quantum entanglement generators often produce pairs at rates too slow for real-time high-speed targeting. The efficiency of these generators must be vastly improved. Furthermore, the signal photons, traveling through the atmosphere, face absorption and scattering by air molecules, water vapor, and particulate matter. This attenuation weakens the returning signal, making detection harder. Advanced error correction algorithms and highly sensitive superconducting nanowire single photon detectors are being developed to catch these faint whispers. Despite these formidable challenges, the pace of advancement in quantum sensing is accelerating rapidly. Major defense contractors and national research laboratories around the world are pouring billions of dollars into this exact field. They understand that whoever masters quantum thermal imaging first will hold a decisive, perhaps insurmountable advantage in future conflicts. We are already seeing the first successful demonstrations of quantum radar principles in ground-based facilities. These early prototypes have successfully detected targets that were completely invisible to conventional radar systems. The next logical step is to miniaturize these systems for airborne platforms, starting with large surveillance aircraft before moving to missiles. As these systems shrink, they will likely first be deployed as auxiliary sensors on advanced fighter jets, working alongside traditional radar and infrared search and track systems. This hybrid approach will allow pilots to cross-reference data, using the quantum sensor to cut through heavy electronic jamming and verify the authenticity of targets detected by other means. The integration of quantum sensors will fundamentally alter the tactics of aerial engagements. Currently, a stealth fighter relies on remaining undetected until it is close enough to launch its weapons. But against a quantum-equipped adversary, that element of surprise is lost. The engagement envelope will expand drastically, as targets can be positively identified from much further. This forces a paradigm shift in aircraft design. If physical invisibility is no longer guaranteed by shape and coatings, future aircraft may need to prioritize extreme speed, maneuverability, and advanced directed energy weapons to survive. The era of the slow, heavily armed stealth bomber might eventually give way to swarms of hypersonic, highly agile combat drones. Moreover, the advent of quantum missiles will spark a completely new arms race in quantum countermeasures. How do you defend against a sensor that cannot be spoofed or jammed? The answer likely lies in quantum cryptography and quantum computing. Future defense systems might attempt to subtly alter the surrounding quantum fields to create localized zones of decoherence. Imagine an active defense system that creates a cloud of quantum noise around the aircraft, intentionally breaking the entanglement of incoming signal photons before they can return to the missile. This would effectively blind the quantum sensor, forcing it back into the realm of classical physics. It is a theoretical concept, but in the quantum age, theory quickly becomes reality. Another potential defense mechanism could involve advanced metamaterials designed to perfectly absorb single photons without reflecting any signal back. While current radar-absorbing materials are designed for macroscopic electromagnetic waves, quantum-absorbing materials would need to operate at the single particle level is a massive leap in material science engineering. The transition to quantum warfare also raises critical questions about artificial intelligence and decision-making speeds. Quantum sensors will generate vast amounts of highly complex, multi-dimensional data. Human pilots simply cannot process this information fast enough. Advanced AI algorithms will be absolutely essential to interpret quantum sensor data in real milliseconds. These AI systems will need to autonomously manage the quantum entanglement rates, filter the incoming photon streams, and instantly distinguish between true targets and quantum anomalies. The integration of quantum sensing with quantum computing could create targeting systems that are effectively prescient, predicting target trajectories with unprecedented mathematical accuracy. We must also consider the ethical and strategic stability implications of such disruptive technology. When defensive measures are rendered obsolete, the incentive to strike first increases dramatically. If a nation knows its stealth fleet can be easily targeted, it might feel compelled to launch preemptive strikes before its adversaries can fully deploy their quantum missile system. This creates a highly volatile geopolitical environment. Arms control treaties and non-proliferation agreements will struggle to keep pace with the rapid development of quantum weapons. How do you regulate a technology that relies on the fundamental properties of light and matter? The verification of quantum capabilities will be incredibly difficult, if not entirely impossible. Despite the risks, the technological momentum is unstoppable. The underlying science of quantum mechanics is solid, and the engineering pathways, while steep, are clearly defined. It is no longer a question of if quantum missiles will become a reality, but rather a question of when and which nation will be the first to successfully field them on the modern battlefield. Let's look closer at the specific mechanisms of quantum thermal imaging. Traditional thermal cameras rely on bolometers or semiconductor detectors that react to the bulk energy of incoming infrared radiation. They measure temperature differences across a scene, but they are easily fooled by materials that mimic the thermal emissivity of the background, acting as thermal camouflage. Quantum imaging, however, can exploit a technique called quantum illumination. In this setup, the entangled photon pairs are split. The signal photon is sent towards the suspected target area, which might be heavily obscured by thermal noise or deliberate jamming. The target reflects a tiny fraction of these photons back, mixed with an overwhelming amount of background light. To a classical detector, this returning signal is completely lost in the noise, but the quantum receiver performs a joint measurement on the returning light and the retained idler photons. Because of the quantum correlation, the true reflected photons will exhibit a distinct statistical signature when measured alongside their entangled partners, revealing the hidden target clearly. This means a quantum thermal imager does not just measure heat, it measures the quantum mechanical relationship between the emitted light and the reflected light. This allows it to extract high-resolution images from incredibly noisy environments. It can literally see the shape and structure of a heat source, not just a blurry, glowing blob on a traditional infrared screen. Imagine a stealth fighter deploying a highly advanced towed decoy. This decoy is designed to emit a thermal signature identical to the jet's engines, pulling the incoming classical missile away. A quantum missile, however, would illuminate both the jet and the decoy. It would analyze the returning photons and instantly recognize the physical structural differences between them. The quantum sensor would see that one heat source is attached to a large aerodynamic airframe, while the other is a small, trailing object. It would ignore the deceptive thermal intensity and lock onto the true physical structure of the aircraft. This structural recognition capability, derived purely from quantum correlations, is what makes this technology so devastatingly effective. Furthermore, quantum sensors operate at incredibly low power levels. Because they rely on single photon detection and entanglement verification rather than blasting massive amounts of electromagnetic energy into the sky, they are inherently stealthy themselves. An aircraft targeted by a quantum radar might not even know it is being painted until the missile is already on its way. Traditional radar warning receivers detect the powerful radio waves emitted by enemy targeting systems. But how do you detect a handful of scattered photons that are probing your airframe? Developing warning systems capable of sensing quantum illumination is another massive challenge for defensive engineers, requiring detectors with sensitivities currently unimaginable in combat. The integration of quantum sensors will also revolutionize missile guidance systems beyond the terminal phase. During the mid-course flight, a quantum-linked missile could maintain a secure, unhackable communication channel with the launching aircraft using quantum key distribution. This ensures that targeting updates cannot be intercepted or subtly altered by enemy electronic warfare. If an adversary attempts to jam the communication link, the quantum state of the transmitted keys will instantly collapse, immediately alerting both the missile and the pilot to the interference. They can then switch to autonomous targeting modes or alternative frequencies. This guarantees the absolute integrity of the data link in the most heavily contested electromagnetic spaces. As we delve deeper into this quantum revolution, it is crucial to understand the specific components that make up these futuristic systems. The heart of any quantum thermal imager is the spontaneous parametric down conversion crystal. This specialized nonlinear optical crystal is where the actual magic of creating entangled photon pairs takes place under intense laser illumination. When a high-energy pump laser beam is fired into this crystal, a very small fraction of the incoming photons split into two lower-energy photons. Due to the strict laws of conservation of energy and momentum, these two newly born photons are perfectly entangled. They share a single, unified quantum state, becoming the signal and idler pairs we discussed earlier in the program. The efficiency of this crystal is currently a major bottleneck. Only about 1 in a billion pump photons actually undergoes this down conversion process. To create a viable weapon system, materials scientists must discover new crystalline structures or engineered metamaterials that can generate entangled pairs at vastly higher rates, flooding the sky with quantum probes. Once generated, the idler photons must be stored while the signal photons travel to the target and back. This requires a quantum memory device. Unlike classical computer memory that stores bits as zeros and ones, quantum memory must preserve the delicate superposition and entanglement of the photons without measuring them, as measurement would instantly destroy the state. Researchers are experimenting with storing these photons in atomic ensembles, such as supercooled clouds of rubidium atoms, or within specialized rare earth dope crystals. These environments essentially freeze the photon's quantum information for a few crucial microseconds, just long enough for the signal photon to complete its round trip at the speed of light. The final critical component is the detector. When the vastly attenuated signal photons return, mixed with background noise, they must be captured with near-perfect efficiency. Superconducting nanowire single photon detectors are currently the leading technology. These tiny wires, cooled to near absolute zero, lose all electrical resistance, becoming incredibly sensitive. When a single photon strikes the nanowire, it briefly breaks the superconductivity, creating a tiny, measurable electrical pulse. This allows the system to register the arrival of individual photons with extraordinary precision. However, maintaining the complex cryogenic systems required to keep these nanowires operational inside a fast-moving missile remains a massive hurdle. The engineering solutions to these problems are pushing the boundaries of applied physics. We are seeing the development of integrated quantum photonics, where all these components, the laser, the crystal, the memory, and the detectors, are miniaturized and etched onto a single silicon chip, much like modern computer processors. This is the path to viable quantum weapons. By moving from bulky optical tables to integrated photonic chips, engineers can drastically reduce the size, weight, and power requirements of the quantum sensor. These robust solid-state devices are much more capable of surviving the extreme vibrations and thermal shocks of a missile launch, bringing the theoretical concepts closer to actual battlefield deployment. This rapid miniaturization mirrors the evolution of early classical radar systems, which started as massive building-sized installations before shrinking down to fit within the nose cone of a fighter jet. The quantum revolution is following a similar trajectory, but at a vastly accelerated pace, driven by immense global competition and unprecedented computational power. So, how will a future aerial engagement actually unfold in the quantum era? Imagine a scenario where a classical stealth fighter is patrolling a contested airspace. Its pilot believes they are invisible, relying on advanced radar-absorbing materials and sophisticated thermal suppression to blend perfectly into the cold, dark background of the high-altitude environment. Miles away, an adversary launches a new generation air-to-air missile equipped with a quantum thermal imaging seeker. As the missile accelerates towards the predicted intercept point, it activates its quantum sensor. A silent, invisible stream of entangled signal photons is broadcast forward, sweeping the sky ahead with mathematical precision, searching for any anomaly. The stealth fighter's radar warning receivers remain completely silent. The quantum probe consists of scattered single photons, far too weak to trigger conventional defensive alarms. The pilot continues their patrol, completely unaware that their aircraft is being meticulously illuminated and analyzed at the subatomic level by an approaching, unstoppable weapon system. Some of the signal photons strike the stealth fighter. Despite the radar-absorbing coatings, the physical structure of the jet reflects a tiny fraction of these photons back towards the incoming missile. These returning photons carry the unforgeable quantum signature embedded within them at the moment of their creation inside the missile's down conversion crystal. The missile's highly sensitive nanowire detectors capture these faint reflections. The onboard quantum processor instantly compares them with the securely stored idler photons. The correlation is confirmed. The system filters out all background thermal noise, solar radiation, and potential electronic jamming, revealing a crystal clear, high-resolution image of the target. The missile's AI targeting system analyzes the structural data, confirming the exact model of the enemy stealth fighter based on its physical geometry, not its suppressed thermal or radar signature. The guidance fins adjust, locking onto the precise center of mass of the aircraft. The terminal intercept phase begins, driven by absolute, unshakable quantum certainty. At the last possible second, the stealth fighter's onboard sensors might finally detect the rapidly approaching physical mass of the missile. The pilot instinctively deploys flares, chaff, and activates the directional infrared countermeasures, flooding the space with intense heat, metallic strips, and blinding lasers in a desperate attempt to break the missile's lock. But it is entirely futile. The quantum sensor simply ignores the blinding lasers and the intensely burning flares. The photons emitted by these countermeasures do not possess the required quantum entanglement with the missile's internal memory. They are instantly discarded by the processor as irrelevant background noise. The missile flies straight through the chaotic defense. The intercept is successful. The multi-million-dollar stealth aircraft, the pinnacle of classical aerospace engineering, is neutralized by a weapon that exploited the fundamental mechanics of the universe. This scenario perfectly illustrates why military planners worldwide view quantum sensing not just as an upgrade, but as a complete paradigm shift in the nature of war. This shift will inevitably force a massive reallocation of defense budget. The billions currently spent on refining radar-absorbing materials and complex thermal exhaust suppression might be redirected towards developing faster, more maneuverable unmanned combat aerial vehicles, or UCAVs, that do not rely on invisibility for survival, but rather on overwhelming speed and numbers. Looking further into the future, the integration of quantum technology will not be limited to just the seekers on missiles. We are moving towards a fully quantum integrated battle space. Entire fleets of aircraft, drones, and satellites will be securely linked via quantum communication networks, sharing real-time, unhackable sensor data across massive global distances. This interconnected quantum web will create an omniscient situational awareness. A quantum radar on a naval destroyer could detect a stealth threat, instantly share the precise quantum-verified coordinates with an airborne UCAV, which then launches a quantum-guided missile to neutralize the target. The speed and coordination of this network will be completely unprecedented. To counter this, adversaries will focus heavily on offensive cyber warfare, targeting the classical computer systems that interface with these quantum sensors. While the quantum link itself might be unbreakable, the traditional software interpreting the data could still be vulnerable to sophisticated malware or AI-driven cyber attacks designed to feed false information to the pilot. We will also see the rise of quantum electronic warfare. Instead of broadcasting high-power radio noise, future jammers might attempt to subtly manipulate the electromagnetic environment to induce rapid decoherence in the enemy's entangled photons. By increasing the fragility of the quantum state, they could effectively blind the quantum sensors before they can lock on. This will require a deep understanding of quantum field theory and the ability to project localized quantum disruptions over vast distances. It is a concept that blurs the line between science fiction and military reality, but major defense research agencies are already laying the theoretical groundwork for these exact types of advanced counter-quantum technology. Another fascinating avenue of research is the development of quantum stealth. If a sensor uses entangled photons to see you, can you use quantum mechanics to hide? Theoretical models suggest that a highly advanced active metamaterial skin could potentially intercept incoming signal photons, measure them, and re-emit spoofed entangled photons back to the enemy sensor. This would require the aircraft to possess its own onboard quantum computer, capable of instantly analyzing the incoming quantum state and generating a perfectly forged response before the decoherence alert is triggered. It is an incredibly complex challenge, effectively requiring the defense to outcompute the offense in real time at the subatomic level during a dogfight. As these technologies mature, the cost of entry into advanced aerial warfare will skyrocket. Only nations with massive scientific and industrial bases capable of sustaining cutting-edge quantum physics research will be able to compete. This could lead to a widening gap between major superpowers and smaller nations, fundamentally altering the dynamics of global security. Furthermore, the dual-use nature of quantum sensing presents unique challenges. The same technology that allows a missile to perfectly identify a stealth fighter can also be used for highly detailed Earth observation, resource mapping, and deep space exploration. The line between civilian scientific advancement and military weaponization will become increasingly blurred. We must prepare for a future where the sky is no longer a place to hide. The development of quantum missiles marks the end of the stealth era as we know it. It forces a complete reimagining of air combat tactics, aircraft design, and global strategic deterrence. The invisible shield has been shattered by the profound and unstoppable power of quantum mechanics. Let's take a moment to review the immense journey we have covered today. We started with the classical principles of aerial warfare, exploring how modern stealth fighters utilize specialized geometry and radar-absorbing materials to defeat conventional radio frequency tracking, and how they manage their massive thermal signatures to evade standard heat-seeking missiles. We examined the intricate dance of countermeasures, from traditional high-heat flares to advanced directional infrared lasers, highlighting how the battle for the skies has historically been a contest of optical deception and electronic noise. A contest where the goal was always to confuse the enemy sensors long enough to complete the mission and survive the engagement. Then, we stepped into the quantum realm, introduced to the strange and powerful concept of quantum entanglement. We learned how particles of light, photons, can be inextricably linked, sharing a secure cryptographic connection that transcends physical distance. This spooky action at a distance is the fundamental key that unlocks the next generation of sensor technology. We saw how quantum thermal imaging utilizes these entangled pairs to cut through the fog of war. By broadcasting signal photons and comparing the reflections against securely stored idler photons, these systems can perfectly distinguish a true target from background noise, thermal decoys, or active electronic jamming, achieving unprecedented levels of targeting accuracy. We discussed the monumental engineering hurdles that still remain. Miniaturizing delicate laboratory equipment, maintaining fragile quantum states in extreme environments, and developing hyper-efficient photon detectors are massive challenges. But the relentless pace of global research and massive defense investments suggest these obstacles will soon be overcome. We explored the profound strategic implications of this technology. The realization that multi-million-dollar stealth fleets could soon be rendered obsolete is forcing a complete paradigm shift in military planning. The focus will likely shift from physical invisibility to extreme hypersonic speed, advanced AI integration, and the development of new quantum countermeasures. We envisioned a future battle space defined by quantum networks, where sensors, drones, and weapons are linked by unhackable communication channels, creating an omniscient and highly lethal combat environment. An environment where the classical rules of engagement are rewritten by the absolute certainty provided by the fundamental laws of subatomic physics. This is not just an incremental upgrade in weapon systems. It is a fundamental transformation in how humanity perceives and interacts with the physical world during conflict. The quantum leap in aerial warfare represents the ultimate triumph of fundamental science over specialized engineering, proving that eventually, the laws of the universe always win out. As we continue to push the boundaries of what is technologically possible, we must also grapple with the ethical and geopolitical consequences. The destabilizing effect of rendering defensive systems obsolete cannot be understated. The world must find new ways to manage arms control and maintain strategic stability in an era where hiding is no longer a viable option. The transition from classical stealth to quantum sensing is a testament to human ingenuity and our relentless pursuit of technological superiority. It reminds us that the battlefield is a constantly evolving landscape, shaped by the deepest mysteries of science. The future of air combat belongs to those who can harness the bizarre and powerful nature of the quantum realm. As we look to the horizon, the skies of tomorrow will be vastly different from the skies of today. The silent, invisible predators of the modern era will inevitably be replaced by systems that see the world not just through heat or radio waves, but through the fundamental, unbreakable connections of quantum mechanics. The game of hide and seek is finally coming to an end. The development of quantum missiles is a stark reminder that in the realm of military technology, complacency is fatal. The nations that cling to the fading promise of classical stealth will find themselves severely disadvantaged against adversaries armed with quantum certainty. The race to master this technology is arguably the most critical arms race of the 21st century. We are witnessing the dawn of a new age, where the abstract equations of theoretical physics are forged into the most advanced and decisive weapons ever conceived. The challenges are massive, the costs are astronomical, but the strategic imperative is absolute. The quantum revolution is here, and it is poised to permanently redefine the meaning of global air superiority. It is a fascinating, terrifying, and awe-inspiring glimpse into the future of human conflict. A future where the microscopic world dictates the outcomes of macroscopic battles. Where the spin of a single photon can determine the fate of a multi-million-dollar aircraft and the lives of the pilots inside. The convergence of physics and warfare has never been more profound. Thank you for joining me on this deep dive into the quantum leap of aerial warfare. The science is complex, but the implications are undeniable. As we continue to monitor the rapid advancements in this field, one thing is absolutely certain. The skies will never be the same again. The era of true invisibility is over, replaced by the era of inescapable quantum clarity. I am Dr. Sachi Vale, and this has been Science Aura. We are dedicated to bringing you the most cutting-edge developments in science and technology, exploring how they shape our world and our future. If you found this exploration of quantum military technology insightful, please consider subscribing to our channel and sharing this video with others who are curious about the future. Your support allows us to continue investigating these complex topics and translating them into comprehensive, accessible narratives. The world of science is moving faster than ever, and we are here to ensure you stay ahead of the curve. Leave your thoughts and questions in the comment section below. How do you think quantum technology will change the future of global security? We read every comment and love engaging with our community of forward-thinking minds. In our upcoming episodes, we will continue to explore the fascinating intersections of quantum mechanics, artificial intelligence, and advanced engineering. We will look at how these technologies are not just changing warfare, but revolutionizing medicine, communication, and energy generation. The universe is full of mysteries waiting to be unraveled, and the tools we are building to understand it are becoming increasingly powerful. From the vastness of deep space to the subatomic intricacies of entangled particles, science is the ultimate adventure. Stay curious, keep questioning the world around you, and never stop seeking the truth hidden in the data.